In this video we'll explore the area of parallelograms. Now one way we can look at this is by actually using dot or grid paper to help us find that area. As we've talked about before, we can use the additivity principle by splitting the parallelogram into shapes that we know, such as triangles and rectangles. So if I draw two vertical lines here, I can see that I have two triangles and one rectangle, and those are easy to find the area for. So if I find the area of each, that would be the first one's 1/2 of 2 units by 4 units. The area of the rectangle is 2 units by 4 units. And the area of this other triangle is 1/2 the 2 times 4 as well. And if I add all three of those areas together, I would get 16. Now if you notice here, one of the interesting things about the parallelogram is that triangle 1 and triangle 3 have the same area. So in essence, one thing I could do is actually use the moving principle as well. Say I draw that line right here and look at area 3. I can actually cut that off and move it to the other side, and I can see now I have a rectangle. In this case, a special rectangle, a square. So that then I'm actually looking at the length times the width, which is 4 times 4 is 16. And that's how we actually lead into the formal formula for the parallelogram. And the formal formula states that we're looking at the base times the height of the parallelogram to give us area. Where base is the length of a chosen side for the parallelogram. You could choose any of the 4 sides. The height's going to be the perpendicular distance to the opposite side. So let's look at this parallelogram. And this one we use just because make it a little bit different so you can see that it's still always true depending on which side you use. So if I use AD as my base, because that's a nice side to use since I can actually count the units, I can see that that base is 5 units. 1, 2, 3, 4, 5 centimeters. And then if I want to create the perpendicular, I'm going to go directly across to get that perpendicular segment. And I can count that 1, 2, 3 centimeters. I could have also drawn it from D so that it would be inside here, because I just need to go from one vertex to the other side and be perpendicular to it. So if I multiply then my base times my height, 5 times 3 gives me 15 square centimeters. And if you think about it, if I did draw that line here, I could move this triangle up here and it would fill in that white space. Hence why it'd be 5 by 3. Now it could also choose that diagonal side. It's a little harder to deal with because of the measurements, but the idea is still the same. So say I make DC my base, and I can use a program like GeoGebra to measure and find that's about 3 6/100 centimeters. Or I could use a ruler if I don't have any programs with me. Now I'd want to be perpendicular to this base, so I could either be perpendicular through C or through D. And I use DG, makes a perpendicular line here. And again, it's kind of weird because of that diagonal, but it is perpendicular, so I measure that, again using a ruler or using a program, and I get about 4 1/1600 centimeters. When I multiply my base and my height now, it's a little bit more approximate because my measurements are approximate, but it will come out to about 15 square centimeters as well.